Good morning. Let us see the example based on variational approach. A bar problem wherein the bar is fixed at left hand side and carrying load F on the right hand free end. The degrees of freedom per node is 1 and the nodal displacement per node is indicated over the diagram as U1 and U2 at node 1 and 2. A being the area of cross section of bar and E is the Young's modulus. So the total strain energy is 1 half integral over volume V sigma epsilon dv. So here sigma you have to substitute to be E into strain, therefore it becomes 1 half integral over volume over that along the length of that particular bar to be epsilon square E into a dx, as a dx is nothing but dv. Total strain energy and work potential contribute to the total potential term, total potential energy over here. So you need to express these two now in total potential energy as 1 half integral 0 to L ae du by dx square of the bracket dx plus in bracket minus f1 u1 minus f2 u2 being the work potential. So simplify these terms now. Now you have to assume here polynomial function for displacement to be u as a0 plus a1x. Applying the boundary conditions for this bar now, at x is equals to 0, u is u2, that is a0, and that is equals to u1. So at x is equals to L, u is equals to u2, that is a1, and therefore it is equals to u2 minus u1 by L. So this is a1. So both these values now you have to substitute in the polynomial function u. So u becomes equals to u1 plus in bracket u2 minus u1 by L into x. So derivative of this u is u2 minus u1 by L. Now potential energy equation you have to write as, you have to replace now du by dx term by the new term now u2 minus u1 by L in that potential energy equation. So integrating this equation, you will get ae by 2l in bracket u1 square plus u2 square minus 2 u1 u2 minus f1 u1 minus f2 u2. Now you need this total potential to be minimized by minimization of this potential means small change in potential energy with respect to that nodal unknown, you have to equate it to 0. So differentiating this potential energy with respect to u1 first of all and equating it to 0, you will get one equation as ae by L minus u1 plus u2, that is equals to f2, and again the second differential with respect to u2 yield the second equation as ae by L u1 minus u2 equals to f1. So these two equations can be put in a matrix form, which is the similar equation as we are discussed using a direct equilibrium approach also, that is direct force approach, direct approach as the first approach. So this is the equation based on variational approach. So in standard form that equation and the stiffness matrix is given as similar to earlier case. The last approach is the Galerkin approach, that is based on weighted residual terms. So the boundary value problems are solved by Galerkin method without converting into variational form. So it works directly on differential equation, that is strong form. So u being the known scalar function, L is the linear, the non-linear differential operator, u being the scalar function defined over domain D. Boundary conditions are also given. So this is approximated to be a weighted sum of the independent functions, and that equation is defined like this as u equals to psi naught plus summation from I equals to 1 to n ai psi I. Here u being the function of x satisfying boundary conditions, psi naught is the necessary function, ai are the coefficient terms, and psi I are the ith basis function. So substituting approximate function, we can get the domain residual term over here. So bracketed term is u now in this case, lu plus f like this. So you have to minimize this domain residual and find ai by making this weighted residual integral equals to 0. So the final form of this particular Galerkin method is like this as integral over domain D r multiplied by psi I multiplied by dd, and you have to equate it to 0. So this will yield n simultaneous equations that you have to solve the unknown coefficients and finally to get the approximate function. This is overall about the Galerkin approach. So for Galerkin approach, you have to remember this equation as integral over domain D r psi I dd, that is equals to 0. That's all.